IPv4 addressing is a fundamental aspect of computer networking that plays a crucial role in enabling communication between devices on the Internet. While the adoption of IPv6 is steadily increasing, IPv4 continues to be widely used in networks worldwide, particularly in private networks. The migration from IPv4 to IPv6 is a gradual process that will take years to complete, making a thorough understanding of IPv4 addressing essential for network professionals. In this discussion, we will delve into the intricacies of IPv4 addressing, exploring its header format, the concept of subnetting, the different classes of IP addresses, and the purpose of subnet masks. We will also examine the distinction between private and public IP addressing, and how variable length subnet masking, VLSM, allows for greater flexibility in address allocation. By gaining a comprehensive understanding of IPv4 addressing and its related concepts, you will be equipped with the knowledge and skills necessary to navigate and manage networks that still heavily rely on IPv4. So, let's dive into the world of IPv4 addressing and discover its significance in the ever-evolving realm of computer networking. Header format. The IPv4 header serves as a crucial component of every IP packet, encapsulating essential information required for proper routing and delivery of network packets. Within this header, two key elements are present: the source IP address and the destination IP address. An IP address is composed of two distinct parts, the network ID and the host ID. The network ID is located in the high order or leftmost bits of the IP address and is responsible for specifying the network to which a device belongs. It serves as an identifier for a specific network segment or subnet. By examining the network ID, network devices can determine the appropriate path to route the IP packet towards its intended destination network. On the other hand, the host ID is situated in the low order or rightmost bits of the IP address, representing the unique identifier for a specific device within a given network. It helps distinguish individual devices within the same network segment, allowing data to be directed to the correct recipient. By combining the network ID and the host ID, an IP address enables effective communication and data exchange between devices across different networks. Network devices utilize this addressing scheme to route packets accurately, ensuring that data reaches the intended destination. To illustrate the concept of network ID and host ID within an IP address, let's consider the example of the IP address 192.168.10, 10 with a subnet mask of 255.255.255.0. In this example, the IP address 192.168.10.10 represents a specific device within a network. The subnet mask 255.255.255.0 indicates that the first three octets, 192, 168.10, represent the network ID, and the last octet, 10, denotes the host ID. The network ID, derived from the high-order bits, specifies the network to which the device belongs. In this case, the network ID is 192, 168.10. The network ID remains the same for all devices within the network segment, allowing them to communicate with each other directly. The host ID, derived from the low-order bits, differentiates individual devices within the network. In our example, the host ID is 10, signifying the specific device with that IP address within the network segment. The host ID is unique within the network and enables targeted communication between devices. IPv4 was originally designed with a class structure, consisting of classes A, B, C, D, and E. Class D is dedicated to multicasting, while Class E is reserved for experimental purposes. Classes A, B, and C are assigned to network hosts. These classes are further divided into network and host portions, as shown in this figure. The network ID is determined by the high-order bits, while the host ID is determined by the low-order bits. In a classful addressing scheme, networking devices at layer 3 can identify the address class of an IP address by examining the first few bits in the first octet. This class determination allows the device to apply the default subnet mask for the address and identify the host address. Converting between binary and decimal is a fundamental skill when working with IP addressing and understanding network communication. The binary system uses only 2 digits, 0 and 1, while the decimal system uses 10 digits, 0 to 9. Converting between these two numbering systems allows us to represent and interpret IP addresses in different formats. To convert a binary number to decimal, you can follow these steps. 1. Assign weights to each bit position in the binary number, starting from the rightmost bit. The weights follow a power of 2 pattern, with the rightmost bit having a weight of 2 to the power of 0, the next bit having a weight of 2 to the power of 1, the next bit having a weight of 2 to the power of 2, and so on. 2. Multiply each bit by its corresponding weight. 3. Sum the results of the multiplications to obtain the decimal equivalent. Let's take an example, converting the binary number 1101 to decimal. The weight assignment would be 2 to the power of 3, 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0. Now, multiply each bit by its weight. 1 multiplied by 8 plus 1 multiplied by 4 plus 0, multiplied by 2 plus 1 multiplied by 1 equals 8 plus 4 plus 0 plus 1 equals 13. Therefore, the binary number 1101 is equivalent to the decimal number 13. To convert a decimal number to binary, you can use the following steps. 1. Divide the decimal number by 2. 2. Record the remainder, 0 or 1. 3. Divide the quotient obtained in step 1 by 2. 4. Again, record the remainder, 5. Repeat steps 3 and 4 until the quotient becomes 0. 6. The binary representation is obtained by writing the remainders in reverse order. Let's take an example. Converting the decimal number 25 to binary. Dividing 25 by 2, we get a quotient of 12 and a remainder of 1. Dividing 12 by 2, we get a quotient of 6 and a remainder of 0. Dividing 6 by 2, we get a quotient of 3 and a remainder of 0. Dividing 3 by 2, we get a quotient of 1 and a remainder of 1. Dividing 1 by 2, we get a quotient of 0 and a remainder of 1. Writing the remainders in reverse order, we get 11001. Therefore, the decimal number 25 is equivalent to the binary number 11001. Converting between binary and decimal is crucial when working with IP addresses and subnet masks. It allows us to interpret and manipulate these values effectively, enabling proper network configuration and communication. You can practice this skill by exploring binary conversion tricks, tips, and games available online. The Cisco Learning Network offers a fun game for practicing binary conversion at this link. Subnet masks always consist of a series of 1 bits, followed by a series of 0 bits. The boundary where the series transitions from 1s to 0s determines the separation between the network and host portions. Devices operating at layer 3 use this boundary to determine the network address of a packet. They locate the position where the series of 1 bits ends and the series of 0 bits begins. With a default subnet mask, determining the network address for an IP address is straightforward. For example, when a router receives a packet destined for 192.168.1.51, it can determine the network address by performing a logical AND operation between the IP address and the subnet mask. According to the ANDing rules, a 1 and a 1 results in 1, while all other possibilities yield 0. This table illustrates the results of this ANDing operation. It is important to note that the host bits in the last octet are disregarded. In modern networks, the bit boundary can occur at any position within the 32 bits. This table provides an overview of values for the last non-zero octet in a subnet mask. To alleviate the demand for IP addresses, RFC 1918 introduced the concept of private internets, reserving specific address ranges for their use. The following address ranges are reserved for private networks. Class A, 10, 0.0, 08, 10.0.0.010.255.255.255. Class B, 172, 16.0, 012, 172.16.0.0, 172, 31.255.255. Class C, 192, 168.0, 016, 192.168.0.0, 192.168.255.255. These private addresses are commonly used within non-public intranets instead of globally unique public addresses. This approach offers flexibility in addressing design. Any organization can benefit from utilizing an entire Class A address, 10.0.008. To enable communication with the public internet, Network Address Translation, NAT, is employed to translate private addresses to public addresses. By leveraging NAT and assigning multiple private addresses to a single internet routable address, companies can operate with a minimal number of public addresses. Further details on NAT operation and configuration will be in future videos. Subnetting methodologies may vary, but the following 4-step approach is often utilized. Step 1. Determine the number of bits to borrow based on the host requirements. Step 2. Calculate the new subnet mask. Step 3. Determine the subnet multiplier. Step 4. List the subnets, including the subnetwork address, host range, and broadcast address. To illustrate this approach, let's consider an example. Assume we have the network address 192.168.1.0 with the default subnet mask 255.255.255.0 or /24. In this case, the first 24 bits represent the network bits. Suppose we need 30 hosts per network and aim to create as many subnets as possible within the given address space. With these network requirements, we can proceed to subnet the address space. Step 1. We start with a /24 subnet, which has 8 host bits remaining, 32 minus 24. To accommodate 30 hosts, we need to leave 5 bits. Using the formula 2 to the power of b minus 2 equals to number of host addresses, where b represents bits left in the host portion, we find that 2 to the power of 5 minus 2 equals to 30 host addresses. Since 3 bits remain in the original host portion, we can borrow all 3 bits to create as many subnets as possible, by using the formula 2 to the power of r equals to number of subnets, where r represents bits borrowed from the host portion. We find that 2 to the power of 3 equals to 8 subnets can be created. Step 2. The original subnet mask is /24, 255.255.255.0. We add the 3 borrowed host bits to the 24 bits, resulting in a new subnet mask of /27, 255.255.255.224. Step 3. The subnet multiplier can be determined by subtracting the last non-zero octet of the subnet mask from 256. In this case, the last non-zero octet is 224, so the subnet multiplier is 256 minus 224 equals to 32. Step 4. Listing the subnets, host ranges, and broadcast addresses helps visualize the address flow within the address space. The following table presents the subnet addressing scheme for the 192.168.1.0/24 address space. This table showcases the 8 subnets created, each with its respective network address, first usable address, last usable address, and broadcast address. The address space is effectively divided, allowing for efficient addressing and network management. Subnetting example 1. Given the address space 172.16.0.0/16, subnet it to provide at least 80 host addresses per subnet while creating as many subnets as possible. Step 1. We have 16 host bits. Leaving 7 bits for host addresses, 2 to the power of 7 minus 2 is equal to 126 host addresses per subnet. We borrow the first 9 host bits to create as many subnets as possible. 2 to the power of 9 is equal to 512 subnets. Step 2. The original subnet mask is /16, 255.255.0.0. By turning on the next 9 bits starting from the second octet, the new subnet mask becomes /25, 255.255.255.128. Step 3. The subnet multiplier is 128, which can be determined by subtracting the last non-zero octet of the subnet mask from 256. 256 minus 128 is equal to 128. For step 4, this table lists the subnets, their host ranges, and broadcast addresses. Subnetting example 2. Given the address, space 172.16.0.0/16, subnet it to provide at least 80 subnet addresses. Step 1. We have 16 host bits. To create at least 80 subnets, 2 to the power of 7 is equal to 128 subnets. We borrow the first 7 host bits. This leaves 9 bits for host addresses, resulting in 2 to the power of 9 minus 2 is equal to 510 host addresses per subnet. Step 2. The original subnet mask is /16, 255.255.0.0. By turning on the next 7 bits starting from the second octet, the new subnet mask becomes /23, 255.255.254.0. Step 3. The subnet multiplier is 2, which can be determined by subtracting the last non-zero octet of the subnet mask from 256. 256 minus 254 is equal to 2. For step 4, this table lists the first 3 subnets, host ranges, and broadcast addresses. Subnetting example 3. Given the address, space 172.16.10.0/23, Subnet it to provide at least 60 host addresses per subnet while creating as many subnets as possible. Step 1. We have 9 host bits, leaving 6 bits for host addresses. 2 to the power of 6 minus 2 is equal to 62 host addresses per subnet. We borrow the first 3 host bits to create as many subnets as possible. 2 to the power of 3 is equal to 8 subnets. Step 2. The original subnet mask is /23, 255, 255, 2540. By turning on the next 3 bits, starting from the last bit in the second octet, the new subnet mask becomes /26, 255, 255, 255, 192. Step 3. The subnet multiplier is 64, obtained by subtracting the last non-zero octet of the subnet mask from 256. 256 minus 192 is equal to 64. For step 4, this table lists the subnets, their network address ranges, and broadcast addresses. You may have noticed that the starting address space in subnetting example 3 does not encompass an entire classful address. In fact, it represents subnet 5 from subnetting example 2. This scenario demonstrates the concept of variable length subnet masking, VLSM, which involves subnetting subnets. VLSM allows for customized subnets tailored to specific network requirements. The subnetting process remains the same. However, it needs to be performed multiple times to achieve the desired addressing scheme without overlapping address spaces. The recommended approach is to begin with the largest host requirement, create a subnet for it, and subsequently address the next largest host requirement. Let's consider a small example using the address space 172.30.4.0/22 and the network requirements depicted in the figure below. We aim to design an addressing scheme that conserves the most addresses for future growth. We require 5 subnets, 4 LAN subnets and 1 WAN subnet. Starting with the largest host requirement on LAN 3, we proceed to subnet the address space. To satisfy the 250 host requirement, we leave 8 host bits. 2 to the power of 8 minus 2 equals 254 hosts per subnet. With a total of 10 host bits, we can borrow 2 bits to create the initial round of subnets. 2 to the power of 2 equals 4 subnets. The starting subnet mask is /22, 255, 255, 252, 0. By turning on the next 2 bits in the subnet mask, it becomes /24, 255, 255, 255, 0. The subnet multiplier is 1. The 4 subnets are as follows. To satisfy the 100 host requirement, we leave 7 bits. 2 to the power of 7 minus 2 equals 128 hosts per subnet. Since we have 8 host bits in total, we can only borrow 1 bit to create the subnets. 2 to the power of 1 equals 2 subnets. The starting subnet mask is /24, 255, 255, 255, 0. By turning on the next bit in the subnet mask, it becomes /25, 255, 255, 255, 128. The subnet multiplier is 128. The 2 subnets are as follows. To satisfy the 60 host requirement, we leave 6 bits. 2 to the power of 6 minus 2 equals 62 hosts per subnet. With a total of 7 host bits, we borrow 1 bit to create the subnets. 2 to the power of 1 equals 2 subnets. The starting subnet mask is /25, 255, 255, 255, 128. By turning on the next bit in the subnet mask, it becomes /26, 255, 255, 255, 192. The subnet multiplier is 64. The 2 subnets are as follows. To satisfy the 10 host requirement, we leave 4 bits. 2 to the power of 4 minus 2 equals 14 hosts per subnet. With a total of 6 host bits, we borrow 2 bits to create the subnets. 2 to the power of 2 equals 4 subnets. The starting subnet mask is /26, 255, 255, 255, 192. By turning on the next 2 bits in the subnet mask, it becomes /28, 255, 255, 255, 240. The subnet multiplier is 16. The 4 subnets are as follows. We assign subnet 0 to LAN 2, leaving us with 3/28 subnets, 2/24 subnets, and 2/23 subnets. By employing VLSM, we can optimize subnetting and address allocation, catering to varying network requirements effectively. We hope this video helped you on your journey towards becoming a cybersecurity expert. Remember to subscribe to our channel and turn on notifications so you never miss out on our latest content. And if you found our videos helpful, Please give us a thumbs up and share them with your friends and colleagues. Don't forget to check out the links and description for our Anki flashcards and to donate to St. Jude Children's Research Hospital. Your support can make a real difference in the lives of those in need. Thanks again for watching, and we'll see you in the next video.